she had an emergency in her family. Otherwise, she would like to be here. If she were here, perhaps she would give the lecture in Chinese, so I just say ni hao, and now I speak in English. And this model is CFD. You already heard I don't like CFD, but Jennifer Wen used open foam, which is different from FDS, so perhaps it's okay. She is using a new model, extended discrete reaction model for soot. And I think that is the main element that's maybe different in her work in this paper. And also she's using open foam, which is a model now pushed and developed for fire by FM Global, and she's working with FM Global, and you see her other people, and they couldn't come either, so that's a problem. So explain what the discrete reaction model is, maybe not tell the details of fire foam solver, but that's what she used, and she has some validation studies that I think are pretty significant. Everything he brought. I didn't need my hat. He brought it. So. Went too far. Sorry. Okay. All right. So this is what this discrete reaction model is, and essentially what it does is it represents the combustion over mixture fraction space by several steps in the reaction process. So this one takes you to the end of CO2, but now you can still have CO on the fuel side, and you have soot. So it's using that kind of model to represent, and here's the steps in the reaction process. This parameter here is the air-fuel ratio. So, and these are the ends of this reaction, you know, in each of the steps. So lean, and then very fuel-rich zone. This is like a laminar flamelet model with this reaction put in. The turbulence is expressed by PDF. So people who are numerical modelers know what this is. Those that don't, I cannot explain it because I don't have the time and I don't have the full knowledge. But it's a PDF model that gives a probability distribution for the mixture fraction. And this is the way it's represented. And then if you know the mixture fraction, which you're solving for directly, you can get now the species concentrations for any species, soot, CO2, CO, and that's the basis of this. This is some details on the mixture fraction and how it relates to this other thing called variance, and this is the real mixture fraction, which is the dot product of the gradient of mixture fraction. This is an empirical constant that they use. And now for radiation, they take the absorption coefficient locally as the sum of two pieces. The piece for the soot and the piece from the gases. And for the gases, they use the program RADCAL, which is an old program that tells you how to calculate from spectral analysis of radiation what their contributions are, if you know the concentrations, obviously. This is partial pressure, which is related to concentration. And then for soot, they use this model that relates the soot volume fraction and local temperature. And the soot volume fraction is calculated based on the gas density, the soot carbon density, and the soot concentration in the field. The mass fraction is the soot mass fraction. These are the equations they are solving. They're time or space average equations in the standard turbulent tradition. So they're calculating for mean quantities of the variables in the turbulent sense. And they have mass, momentum, enthalpy, mixture fraction, you see. So they get all the species from just solving the mixture fraction. And people that use this kind of approach understand it. These equations are so-called large eddy simulation, where they decouple the pressure from things like density. So there's no coupling between energy and momentum. So there's some simplifications there. But all of that is standard in this kind of approach. Now, to solve these equations, they use the fire foam solver. If you don't know fire foam, what I understand, it was a student at Imperial College that was working with the old Spaulding group. You might realize that Brian Spaulding, in the history of development of CFD, was like a pioneer in developing models for combustion. And this student, like very smart computer-oriented students, never graduates, just goes out and founds a company like, Microsoft or Facebook or something like that. This student went to his house and founded Fire Foam, and people are using it now. So that's just a little aside. Here's the validation studies. One is small fire, 7 centimeter pool fire. That's almost laminar. Then goes to 1 meter pool fire, which is methane. So that's a gas. And then finally, reduced scale enclosure experiments using methane, heptane, and toluene. Toluene is very, very sooty. Very, very sooty. I used that in my laboratory one time for a demonstration. The fire department came. We had so much smoke it wouldn't even go out the exhaust. So let's take the small fire, and here's some particulars of it. You can see it's methane, that's the flow velocity, the heat release rate, very small, ambient temperature, and then here's toluene for that same fire. And so under normal conditions. Now, radiation model, they use a particular one there, and then in their later studies, they use a slightly different radiation model. But they put some radiation in. So, this nice picture they